So cloud computing, it's this term that rather swept onto the scene in recent years. And it sounds like it's some new and trendy technology. But in reality, it's really just a very nice packaging up of a whole number of technologies that have actually been with us for some time. In fact, cloud computing, in its simplest form, can really be thought of as just outsourcing the hosting of your applications and really outsourcing the hosting of your physical servers to someone else. Put another way, renting space and renting time on someone else's computers. But these days, we just have so much computational capabilities. That is, our computers are so fast, our CPUs are so many, and we have so much RAM that new and fancier technologies have lent themselves to this trend of hosting all the more software and putting all of the more hardware offsite in the so-called cloud so that companies, both big and small, can no longer need to host their own physical hardware or even a whole number of roles in their own local companies. And so what we'll do now is dive into cloud computing, look at some of the problems it solves, look at some of the opportunities it affords, but ultimately take a look from the ground up at what's underneath the hood here so that by the end of this, we have a better understanding of what the cloud is, why it is useful, and what it actually is not. So with that said, let's start with a simple scenario. Of course, the cloud perhaps derives its origins from how the internet for some time was drawn, which was just this big nebulous cloud, in that it doesn't really matter what's inside that cloud, although at this point you most surely appreciate that inside of this cloud are things like routers, and running through those routers are packets, both TCP, IP, and the like. And underneath the hood then of this cloud is some transport mechanism that gets data from point A to point B. So what might those point A's and point B's be? Well, if this here is my little old laptop connected somehow to the internet here, and maybe down here there is some web server on which lives a whole bunch of web pages. Maybe it's my email, maybe it's the day's news, maybe it's some social media site or the like. I, at point A, want to somehow connect to point B down here. Now, it turns out it's not all that hard to get a website up and running on the internet. You can, of course, use any number of languages. You can use any number of databases. And you can do it with relatively little experience just getting something on the internet. In fact, it's not all that hard, relatively speaking, to get a prototype of your application or even your first version of your business up and running. But things start to get hard quickly, especially if you have some success. Indeed, a good problem to have is that you have so many customers and so many users hitting your website that you can't actually handle all of the load. Now, it's a good problem in the sense that at least business is booming, but it's, of course, an actual problem in the sense that your customers aren't going to be able to visit your website and buy whatever it is you're selling or read whatever it is you're posting if your servers can't actually handle the load. And by load, I simply mean the number of users per minute or per unit of time that your website is actually experiencing, and its capacity, meanwhile, would be the number of users it can actually support. Now, why are there these limits in the first place? Well, you may recall that inside of a computer is a CPU, the brains of that computer, and inside of a computer is some memory, like RAM, and there might be some longer-term storage, like hard disk space. At the end of the day, all of those resources and more are finite. You can only fit so much physical hardware in a computer. Humans have only been able to pack so many resources into the physical space of a computer. And then, of course, there's cost. You might be able to only afford so much computing capacity. So if a computer can only do some number of things per second, there's surely an upper bound on how many people can visit your website, how many people can add things to their shopping cart, how many people can check out with their credit card, because you only have, at the end of the day, finite numbers of resources. Now, what does that mean in real terms? Well, maybe your web server can handle 100 users per minute. Maybe it can handle 1,000 users per minute. Maybe it can handle 1,000 users per second, or even much more than that. It really depends on the specifications of your hardware, how much RAM, how much CPU, and so forth that you actually have. And it also depends to some extent on how well written your code is and how fast or how slow your code, your software actually runs. So these are knobs that can ultimately be turned, and through testing, can you figure this out in advance by simulating traffic in order to estimate exactly how many users you might be able to handle at a time. Now, the relevance to today is that the cloud, so to speak, allows us to start to solve some of these problems and also allows us to start abstracting away the solutions to some of these problems. Well, let's see what this actually means. So at some point or other, especially when it's not just my laptop, but it's like 1,000 laptops or 10,000 laptops and desktops and phones and more that are somehow trying to access my server here, at some point we hit that upper limit, whereby no more users can fit onto my website per unit of time. So what is the symptom that my users experience at that point? If I'm over capacity, well, they might see an error message of some sort. They might just experience a spinning icon because the website is super slow to respond. And maybe it does respond, but maybe it's 10 seconds later. So at the end of the day, they either have a bad experience or no experience whatsoever, because my server can only handle so many requests at a time. So what do you do to solve this problem? If one server is not enough, maybe the most intuitive solution is, well, if one server is sort of not giving me enough headroom, why don't I just have 2 servers? So let's go ahead and do that. Instead of having just 1 server, let's go ahead and have 2. And let me propose that on this second server is the exact same software. So whatever code I've written, and in whatever language it's written, I just have copies of my website on both the original server and the second server. OK, now I've solved the problem in the simple sense that I've doubled my capacity. If one server can handle 1,000 people per second, well, then surely 2 servers can handle 2,000 people per second. So I've doubled my capacity. So that's good. I've hopefully solved the problem. But it's not quite as simple as that, right? At least pictorially, I'm still pointing at just one of those servers. So we're going to have to clean up this picture alone and somehow figure out how to get users, or more generally traffic, to both of these servers. Right? I could just naively draw an arrow like this, but what does that actually mean? We don't want to abstract away so much of the detail that we're ignoring this problem. How do we implement this notion of choosing between left arrow and right arrow? Well, let's consider what our solutions might be. If a user like me on my laptop is trying to visit this website, and the website ideally is going to live at something like example.com or facebook.com or gmail.com or whatever, I don't want to have to broadcast different names for my servers, right? And you might actually notice this on the internet. You might notice if you start noticing the URLs of websites you're visiting, especially for certain older, stodgier companies who haven't necessarily implemented this in the most modern way, you might find yourself not just at www.something.com, but if you look closely, you might find yourself occasionally at www.1.something.com or www.2.something.com or even www.13.something.com, which is to say that some companies appear to solve this problem by just giving different names, similar names, but different names to their 2 servers, 3 servers, 13 servers, or however many they have, and then they somehow redirect users from their main domain name, www.something.com, to any one of those 2 or 3 or 13 servers. But this isn't very elegant. The marketing folks would surely hate this because you're trying to build some brand recognition around your URL. Why would you dirty it by just putting these arbitrary numbers in the URLs? Plus, if you fast forward a bit in this story, if for some reason down the road you get fancier, bigger servers that can handle more users, and therefore you don't need 13 of them, you can get away with just 6 of them, well, what happens if some of your customers have bookmarked, very reasonably, one of those older names, like www.13.something.com, so that now when they try to visit that URL, gosh, they might hit a dead end. So you could solve that in some other way, but the point is it would seem to create a problem quickly, and it's just a naming mess. Why actually bother having your users see something as messy as these numbered servers? It would be nice to do this a little more transparently. So how could we do this? Well, let me propose that we kind of need some middleman here, so to speak, whereby traffic comes from people like me on the internet and then either goes to the left or goes to the right, or no matter how many servers we have, goes to one of those actual web servers. So how does this middleman, and to borrow some past terminology, how does this black box potentially work? Well, let's consider some of the building blocks, some of the puzzle pieces we have technologically at our disposal now. You may recall that every server on the internet has an IP address, Internet Protocol address, a unique address for it. And that's, again, a bit of a white lie because there are technologies via which you can have private IP addresses that the outside world doesn't see. But let's stipulate for today's purposes that every computer on the internet certainly has an IP address, whether public or private. So maybe, just maybe, we could leverage an existing technology, DNS, the domain name system, so that rather than only return one IP address of a server when you look up www.something.com, we return the IP address of the server on the left, some of the time, or the IP address of the server on the right some of the time, effectively balancing our load, our traffic across the two servers. And in fact, if you do this 50-50, you can take really what's called a round-robin approach and ideally uniformly distribute your traffic across multiple servers. And what's nice in this model is that because you're using DNS, the user doesn't really notice what's going on. At the end of the day, none of us humans really care what IP address we're actually going to if we visit facebook.com or gmail.com or the like. We just care that our computer can find that server or servers on the internet. So via DNS, we could very cleverly, via this middleman here, which is really just going to be some third device, some separate server, it, as a DNS device, could just respond to requests from customers with either this IP address or this IP address, or any number of different IP addresses. So does this solve the problem? Again, most everything in computer science would seem to be a trade-off at the end of the day. And this seems almost too good to be true, perhaps. It's so simple. It leverages an existing technology. It just works. So what prices might we pay? Well, DNS, it turns out, gets cached quite a bit. And what does caching mean? Caching something means keeping some past answer, or more generally, piece of information around so that you can access it more quickly the second and the third time and beyond. And so computers today, Macs and PCs, as well as servers on the internet, other DNS servers on the internet, for performance reasons, will often remember the responses that they get from DNS servers. For instance, if on my Mac I visit facebook.com, hypothetically a lot of times during the day, it's kind of stupid if my laptop again and again and again and again asks some DNS server for facebook.com's IP address if it already asked that same question an hour ago, or more realistically 2 minutes ago, or something like that. It would be smarter if my operating system, or even my browser, Chrome or Firefox or whatever I'm using, actually remembers that answer for me so that my computer can just pull up that website faster by skipping a step, by not wasting time asking a server again for the IP address of a server. And after all, IP addresses, it turns out, generally don't change that often. It's certainly possible for a company or university or even a home user to change their computer's IP addresses, but the reality is it doesn't change all that often. The common case is to have the same IP address now as you might an hour from now, or even a day or a week or a month from now. But the key thing is that it can change. And especially if you're worried about customers, not just some personal website, but you might lose business. You might lose orders if users can't visit your website. Anything that puts your server's uptime, so to speak, being accessible on the internet at risk, probably is worthy of some consideration. So let me propose then that just one of these servers goes offline somehow. Maybe it's deliberate, you need to do some service for it, or maybe it crashed in some way, or it got unplugged somehow, or something went wrong such that now one or more of your servers across which you've been load balancing no longer can talk to the internet. What might happen? Well, if some customer's Mac, like my own, has remembered or cached that particular server's IP address, that is not a good situation, because your Mac or PC or whatever is going to now try to revisit your website again and again and again at that old cached IP address that apparently can be a dead end. And so even though you still have servers that could potentially handle that customer's request, that customer's order, that customer's desire to check out, he or she really is still not going to be able to visit the website unless that cache expires. Maybe they reboot their computer so that the cache forcibly expires. Maybe they just wait some amount of time so that that IP address is forgotten by the browser or by the operating system or by some other DNS server until the new ones available IP addresses are picked up instead. But there is that risk. And I would argue that this risk is even higher, especially for companies that might be considering moving their infrastructure from one service to another. If you're deliberately going to move your servers from one IP address to another, as might happen if you change cloud providers, so to speak, more on those in a minute. Really, if you change the companies that you're using to host your servers, your IP addresses will change, and you certainly don't want to incur a huge amount of downtime in a situation like that. So there are these trade-offs. Easy solution, technologically pretty inexpensive to do. It just works using existing technology, but you open up yourselves to this risk. All right, so let's address that. Putting back the old proverbial engineering hat, let's try to solve this problem. It seems that giving a unique IP address to this server and to this server, and any number of other servers that are back there, might not be the smartest idea insofar as those IPs can get cached. So what if we use DNS as follows. When my laptop or anyone else's requests the IP address for www.something.com, why don't we return the IP address of this device here, this load balancer, as we'll start calling it, where a load balancer is usually just a physical device or multiple physical devices whose purpose in life is to balance load. Packets come in, and similar in spirit to a router, they do route information to the left, to the right, or some other direction. But their overarching purpose isn't just to get data from point A to point B, but to somehow intelligently balance that traffic over multiple possible destinations for point B, identical servers in the case of our story here. So what if instead we address this problem of potential downtime by returning the IP address of the load balancer, and then, by nature of private IP addresses or some other mechanism that the end user does not need to know or care about, this load balancer somehow routes the traffic to either the first device or the second device, LB here being our load balancer. All right, so we seem to have solved this problem. Insofar as now we have configured our DNS servers to return the IP address of the load balancer, there's no problem of downtime as we described a moment ago, because if server 1 goes offline for whatever reason, no big deal. The load balancer should hopefully just notice that and subsequently start proactively routing all incoming data that reaches its IP address to server 2 and not server 1. Now, how does the load balancer know? Well, either a human could intervene. Maybe someone gets a late night call or text or page saying, uh-oh, server 1 is down, you better do something. And then he or she can manually configure the load balancer to no longer send any traffic to server 1. That seems kind of stupid in an age of automation and smart software. Maybe we can do better. And indeed, we can. A technique that's often used by servers is something modeled from the human world, to use what you might describe as heartbeats, to actually configure the load balancer and servers 1 and 2 to operate as follows. Maybe every second, every half a second, maybe every 5 seconds, you configure server 1 and server 2 to send some kind of heartbeat message to the load balancer. This is just like a TCP/IP packet, some kind of network packet that's the equivalent of saying, I'm alive, or more goofily, like boom, 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 ergo the heartbeat metaphor. But the point is that 1 and 2 and any number of other servers should be configured to just constantly reassure the load balancer that they are alive, they are accessible, they are ready to receive traffic. And the load balancer, similarly, and you might see where this is going, can very simply be configured to listen for that heartbeat. And if it ever doesn't hear a heartbeat from server 1 or server 2, it should just assume that something's wrong. The server has died. It's gone offline. Something bad has happened. So the load balancer subsequently should simply not route any traffic to that particular server until some human or some automated process brings the server back alive, so to speak, and the heartbeat resumes. Now, of course, this problem doesn't go away permanently. If servers 1 and 2 stop emitting a heartbeat, we really have no capacity for users, but that would be an extreme scenario. Hopefully, it's just one or few of our servers go offline in that way. So we can configure our servers with these heartbeats, which is, think about it, a very simple sort of physiologically inspired solution to a problem. And even if it's not obvious how you implemented it in code, it really is just an algorithm, a simple set of instructions with which we can solve this problem. And yet, damn it, we've introduced a new problem. And so this really is the old sort of leaky hose, where just as we've plugged one leak or solved one problem, another one has sprung up somewhere else along the line. So what's the problem now? What's the problem now? The whole motivation of introducing server number 2, in addition to server number 1, was to make sure that we have enough capacity, and better yet, to make sure that if server 1 or server 2 goes offline, the other one can hopefully pick up the load, unless it's a super busy time with lots and lots of users visiting all at once. So in fact, the general idea at play here is high availability, ensuring that if one server goes down, you have other servers that can pick up the load. Being highly available means you can be tolerant to issues like that. And then load balancing, of course, is just the mere process of splitting the load across those two endpoints. But we have introduced another problem. This might be abbreviated SPOF, or more explicitly, single point of failure. And just as I've solved one problem by introducing this load balancer, so have I introduced a new problem, which is this. There is now, as you might infer from the name alone, a single point of failure. It's fine that I can now tolerate server 1 or server 2 going down, but what can I not tolerate, clearly? What if the load balancer goes down? So this is a very real concern. Maybe the load balancer itself gets overloaded. Maybe the load balancer itself has some kind of issue. And if the load balancer goes down, it doesn't matter how many web servers I have down here or how much money I've spent down here to ensure my high availability. My server is offline if the single point of failure indeed fails. Now, you'd like to think that the load balancer, especially since it only has one job in life, can at least handle more traffic than an individual server. Indeed, clearly, it must be the case that the load balancer is fast enough and capable enough to handle twice as much traffic as any individual server. But that's generally accepted as feasible insofar as your website, your real intellectual property, is probably doing a lot of work, talking to a database, writing out files, downloading things, or any number of other features that just take more effort than just routing data from one server to another, as a load balancer does. But it doesn't matter how performant it is. If the load balancer breaks, goes offline for some reason, your entire infrastructure is inaccessible. So how do we solve this? How do we go about and architect a solution to this? Well, how did we address this issue earlier? We addressed the issue of insufficient capacity or potential downtime by just throwing hardware at the problem. And so maybe we could do that same thing here. Maybe we could just introduce a second load balancer. I'll call this LB as well. And now we somehow have to, I feel like we're just kind of endlessly going to be adding more and more rectangles to the picture. But somehow we need to be able to load balance across now 2 servers and 2 load balancers. So how do we do this? Well, let me clean this up so that we have a bit more room to play with here, and consider how a pair of load balancers might actually work. So if my first server is here and my second server is here, and I'm proposing now to have 2 load balancers, one here and one here, surely both of these have to be able to talk to both servers. So we already have this necessity. And somehow traffic has to come from the internet into this set of load balancers, but probably only to one, because we don't want to solve this with DNS and just have 2 IP addresses out there, because if one breaks, so we can recreate the same problem as before if we're not careful. So what if we do this? What if we use this building block of heartbeats in another way as well? What if we ensure that our load balancers, plural, have just one IP address, which a moment ago seemed to create a single point of failure, but what if we do this? What if we also allow the load balancers to talk to communicate over a network with each other, so that one of the load balancers is constantly saying to the other, I'm alive, I'm alive, I'm alive. And so what the load balancers could be configured to do is that only one of them operates at any given point in time. But if the other server, the other load balancer, no longer hears from that primary load balancer because of the heartbeats that are ideally both being emitted in both directions so that they can both be assured of the other's uptime, if the secondary load balancer stops hearing the primary load balancer, the secondary load balancer can just presumptuously reconfigure itself to take on that one and only IP address, effectively assuming that the first load balancer is not going to be responding to any traffic anyway, and the second load balancer can simply take on the entire load itself. But the key difference now in this particular solution is that there's only one IP address that describes this whole architecture, only one IP address between the 2 load balancers, so we don't risk those potential dead ends that we had a little bit ago with our back-end servers. And so now it's starting to get more robust, more highly available. So that's pretty good. We've solved most of these problems. We've sort of generously, though, swept one problem underneath the rug, whereby every time I draw another rectangle, not just the first time, but now the second time, and add some interconnectivity somehow among them, someone somewhere is spending some money. And indeed, I am solving these problems thus far by throwing money at the problem. And frankly, introducing complexity. And we already look at how many arrows or edges there are now, which might simply refer to physical wires, which is fine. But there's also a logical configuration that's now necessary. And God forbid we have a third load balancer for extra high availability, or any number of servers here, 13 or 20 or 100 or 1,000 servers. It's a lot of cross connections, not just physically, but logically in terms of the requisite configuration. So this complexity does add up, and the cost certainly adds up. And now, once upon a time, and not all that long ago, if a company wanted to architect this kind of solution, you would literally buy 2 load balancers, and you would buy 2 or more web servers, and you would buy the requisite physical Ethernet cables to interconnect the two, and you'd probably buy a whole bunch of other hardware that we've not even talked about, like firewalls and switches and more. But you would physically buy all of this hardware, you would physically connect all of this hardware, and configure it to implement these several kinds of features. But the catch is that the more and more hardware you buy, just probabilistically, the more and more you invite some kind of failure. Maybe it's some stupid human error, but more realistically, one of your hard drives is going to fail. And a hard drive are typically rated for the enterprise in terms of mean time between failure, MTBF, which generally means how long should you expect a hard drive to work on average before it fails. It breaks. It just stops working. So if you have a whole bunch of servers, each of which has a whole bunch of hard drives, at some point, combinatorically, one or more of those drives is just going to fail, which is to say you're going to have a problem and you're going to have to fix it yourself. At some point, too, you're going to run out of physical space. In fact, perhaps one of the most constraining resources, especially for startups, is the physical space itself. You probably don't want to start housing your servers in your physical office because you need a special room for it typically, with enough cooling, with enough access, with enough electricity, and enough humans to actually maintain it. Or you graduate from your own office space and go to a data center, a co-location facility, whereby you maybe rent space in a physical cage with a locking door, inside of which you put racks of servers, just racked up on big metal poles, and you pack as many servers in there as you can. But at some points, you're going to bumping up against other constrained resources: physical space, actual power capacity, cooling, as well as the humans to actually run this. And so very quickly does operations, ops, so to speak, become an increasing cost and an increasing challenge. And one of the most alluring features of the cloud, so to speak, is that you can move all of these details off-site. And you can abstract many of these, let's say, implementation details away, whereby you yourself don't have to worry about the physical wires. You don't have to worry about the make and model of servers that you're buying. You don't have to worry about things actually breaking, because someone else will deal with that for you. But you have to still understand the topology and the architecture and the features that you want to implement, so that you can actually configure them in the cloud. So what do you actually get from cloud providers? There's any number of them out there these days, but perhaps 3 of the biggest are Amazon, Google, and Microsoft, all of whom offer these days a very similar palette of options. And it's outright overwhelming if you visit each of their websites just how many cloud products they offer. But they would generally offer a number of standard products in the cloud. For instance, a virtualized server. So you don't have to physically buy a server these days and plug it into your own Ethernet connection, your own internet connection in your own office. You can instead essentially rent a server in the cloud, which is to say that Amazon, Google, Microsoft, or any number of other companies will host that server physically for you, and they will take care of the issues of power and cooling. And if a hard drive fails, they will go remove the old one and plug in the new one, and ideally they will provide you with backup services. But more sophisticated than that, they can also help us recreate in software this kind of topology. In other words, even without having a human physically wire together this kind of graph, so to speak, that we've been building up here logically, thanks to software these days, you can implement this whole paradigm not with physical cables, not with physical devices, but with software virtually. What does that mean? It means that humans, over the past several years, have been writing software that mimics the behavior of physical servers. Humans have been writing software that mimics the behavior of a router. Humans have been writing software that mimics the behavior of a load balancer. And by implementing mimics the behavior of, really, we are just building in software what historically might have been implemented entirely in hardware. And even that's a bit of an oversimplification, because even when something is bought as hardware, there is, of course, software running on that hardware that actually makes it do something. But they're no longer dedicated devices. You can use generic commodity PC server hardware, really, and transform that hardware into a certain role: a back-end web server, a back-end database, a load balancer, a router, a switch, any number of other things. And so what you are getting from companies like Amazon and Google and Microsoft and more is the ability to build up your infrastructure in software. In fact, the buzzword here, the acronym, is IaaS, Infrastructure as a Service. So you sign up for an account on any of those companies' cloud services websites, and you put in your credit card information or your invoicing information, and you literally, via a command line tool, so a keyboard, or via a nice web-based graphical user interface, GUI, do you point and click and say, give me 2 servers and 1 load balancer. Or if you have enough money in the bank, you say, give me 2 servers and 2 load balancers configured for high availability. Or better yet, you don't say any of that. You just tell the provider, give me a web server and give me a load balancer, and you deal with the process of scaling those things as needed. In fact, a buzzword du jour is auto-scaling, which refers to a feature implemented in software whereby if a cloud provider notices that your servers are getting a lot of traffic, business is good, or it's the holiday season, and you are bumping up against just how many users your 1 or 2 or 3 or more servers can handle, auto-scaling is a feature that will enable the cloud provider to just turn on virtually more servers for you, so that you go from 2 to 3 automatically. You can be happily asleep in the middle of the night, and even though your traffic is peaking, doesn't matter, your architecture is going to auto-scale. And better yet, especially financially, if the cloud provider notices maybe 12 hours later, oh, all of your customers have gone to sleep, we don't really need all of this excess capacity, or maybe the holidays are now in the past, you really don't need this excess capacity, auto-scaling also dictates that those servers can be virtually turned off. So you're no longer using them, you're no longer load balancing to them, and most importantly, you're no longer paying for them. So this is a really, really nice value add at this point. There's no human crawling around on the floor rewiring things and plugging in new servers. There's no finance person having to approve the PO to actually order more servers just to increase your capacity. And most importantly, there's no latency between the time when you notice, oh my God, we're getting really successful and can't handle our load, uh-oh, it's going to be a 2-3 week lead time before we can even get in the more servers. Thanks to cloud computing, you can literally log into Amazon's, Google's, Microsoft's website and click, 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 have more server capacity within seconds, within minutes, far faster than the physical world traditionally allowed. So those are just some of the features now that we gain from outsourcing to the so-called cloud. So where does some of this capability come from? Well, it turns out that over the past many years, humans have been getting better and better and better at packing more physical hardware into the same form factor, into the same physical space. So at the level of CPUs, the brains of a computer, we humans have gotten much better at packing more and more transistors, for instance, onto a CPU. And transistors are little switches that can turn things on and off, 0 and 1, 1 and 0. So you can store more information and you can do more with that information more quickly. CPUs today also have more cores, which you can think of as mini CPUs inside of the main CPU, so that a computer with multiple cores can literally do multiple things at a time. But the funny thing is that we humans, over the past decade or two, really haven't been getting fundamentally faster at life. At the end of the day, I can only check my email so quickly. I can only post on Facebook so quickly. I can only check out from Amazon so quickly, because we humans have, of course, a sort of finite speed to ourselves. We're not doubling in speed a la Moore's Law every year or two. So we have, it would seem, a lot of excess computing capacity these days. Computers are getting so darn fast, we don't necessarily know what to do with all of these CPU cycles and with all of the RAM that we can fit into the same physical box at half of the price that it cost us last year. And so manufacturers and companies realized that, we could actually build a business on this increased capacity. We can implement the computer equivalent of time sharing so to speak, which has long been with us in the history of computing, but we can do this on a much more massive scale now by taking one physical server that has maybe 2 CPUs or 16 CPUs or 64 CPUs and maybe gigabytes and tens of gigabytes or hundreds of gigabytes of RAM all inside of the same physical device, plug it into an internet connection, and then run special software on that one server that creates the illusion that there's multiple servers living inside of that box. And this virtualization software is implemented by way of software called a virtual machine or virtual machine monitor, or another word might be hypervisor. There's different ways to describe essentially the same thing, but a virtual machine is a piece of software running on a computer inside of which is running some other operating system typically. So you might have one server running Windows, but inside of that server are multiple virtual machines, each of which itself is running Windows. So you might be able to chop up one computer into 10 or even into 100. Or perhaps more commonly, you might have a server running Linux or some Unix-based operating system, also with virtual machines on it. But those virtual machines might be running Linux themselves or Unix or Windows or any number of versions of Windows. And so this is the beauty when you have so much excess capacity and so many available CPU cycles and so much RAM, you can kind of slice that up and then sell portions of the server's capacity to customers. And if you're really clever, you might look at your customers' usage patterns and realize that, you know what, it's not necessarily as simple as just taking my server and dividing it up into n different slices, where n is a generic variable for number, and then selling it or renting that space really to end customers. Because you know what? Some of those customers might have some booming businesses, which is great. But some of those customers might not have many users. Maybe it's a few dozen, maybe it's a few hundred, but it's really a drop in the bucket. So instead of selling my computing resources to just end customers, maybe I'll sell it to twice as many customers or 3 times as many customers and essentially oversell my server's capacity, but expect that on average this is just going to work out because some customers will be using a lot of those cycles because business is good, and some won't be because it's just they don't have many customers, or really it's a personal website that doesn't get much usage anyway. And so for some time, has there, of course, been this risk when you sign up for a web hosting company or a cloud provider that your website actually might get really slow for reasons outside of your control. If you are co-located on a server that some other booming business is on, your users might actually suffer if your web host has oversold itself. And so, in fact, this is one of those situations where you get what you pay for. If you're Googling around and finding various cloud providers or web hosting companies more specifically, you might be able to find a deal like $10 per month or $50 per month as opposed to $100 or $200 or more per month. And you do get what you pay for because those fly-by-night operations that are selling you space and capacity super cheaply probably are overselling and overcommitting. So these are the trade-offs too, just how much money do you want to save versus how much risk do you actually want to take on. Generally, it's safer to go with some of the bigger fish these days, certainly when building a business, as you might on a company like Amazon or Google or Microsoft or derivatives thereof. So just to paint a more concrete technical picture of what virtualization is, here's a picture, as you might think of it. So you have your physical infrastructure here. So that's the actual server from Dell or IBM or whoever. Then you have the host operating system, which might be Windows, but is often Linux or some variant of Unix instead. And then you have the hypervisor. This is the piece of software that you install on your server that allows you to run multiple virtual machines on top of it. And those virtual machines can each run any number of different operating systems themselves, or even different versions of operating systems. And so depicted here up top are the disparate guest OSs, operating systems that might be on there. Maybe this is Linux and Solaris, and this is Windows itself, or any number of other combinations. Whatever your customers want, or whatever you want to provide, or essentially rent to customers, you can install. But you do pay a price. So as beautiful as this situation is, and as clever as it is, that we're leveraging these excess resources by slicing up one server into the illusion of, in this case, 3, or more generally more, there's some overhead. Because this hypervisor has to be a middleman between your guest operating systems and your host operating system, the one actually physically installed the server. And any layers of indirection like this, so to speak, have got to cost you some amount of time. If there's some work being done here and you only have a finite number of resources, the hypervisor itself is surely consuming some of your resources. And gosh, this just seems really inefficient, especially if all of your customers are using the same operating system. My God, why do you have to have copies of the same OS multiply installed? This just doesn't feel like it's leveraging much economy of scale. And so it turns out there's a newer technology that's gaining steam, and this is known not as virtualization per se, but containerization, the most popular instance of which is perhaps a company called Docker. And the world of Docker is a little shorter. It's a little smarter about how resources are shared. You still have your infrastructure, your physical server, and you still have your host operating system, whether it's Linux or Unix or something like that. But then instead of a hypervisor, you have the Docker engine, which is really just an equivalent of that base layer of software. But notice what's different. In this case here, we've kind of collapsed the previous picture. In fact, thanks to our friends at Docker who put this together here. The guest OS has disappeared, and you instead have your different applications and your different binaries and libraries, as this abbreviation means, all running on the Docker engine. Now, what does this mean? This means when running Docker, you typically choose your operating system, for instance, Ubuntu Linux or Debian Linux or something else altogether, and then you essentially share that one operating system across multiple containers. Instead of virtual machines, we now have containers. So in other words, you ensure that your different slices all share some common software, the kernel, so to speak, the base core of the operating system. But then you uniquely layer on top of that base system, that base set of default files, whatever customizations your customers or you yourself want, but you share some of the resources. And long story short, what this means is that containers tend to be a little lighter weight. There's less waste of resources because there's less overhead of running them, which is to say that you can generally start them even more quickly. And better yet, you can still isolate your different products and your different services, database and web server and email server and any number of other features, all within the illusion of their own installation, their own operating system, even though there are some shared resources here. So this too has been made possible by the capabilities of modern hardware and the cleverness, frankly, of humans in actually finding solutions or creative uses for those available resources. But what other features or topics come into play in this world of cloud computing? We talked about availability and caching and costing, really figuring out where we're going to actually spend our money by throwing hardware at problems and scaling more generally. But there's also issues of replication, which actually do relate to high availability, so to speak. But replication refers to duplication of data, and really backups more generally as a topic. And then there's also some other funky acronyms that are very much in vogue these days. Besides infrastructure as a service, there's also platform as a service, PaaS, or software as a service, SaaS. Now, SaaS, even if you've not used it under this name, odds are you have been using it. If you do use Gmail or Outlook.com or any web-based email service, you are using software as a service. You don't really know or need to care where in the world your emails physically live or how many servers they're spread across or how your data is backed up or, for that matter, when you click send, how the email even gets from point A to point B. You are treating Gmail and Outlook as a software as a service, with all of the underlying implementation details abstracted away. You just don't know or care how it's implemented. Well, at least if everything's working, you probably do care if something goes down. But there's this intermediate step between this extreme form of abstraction, where all you see is just the top-level service, and the lowest level implementation that we've discussed, which is infrastructure as a service, whereby when using something like Amazon, you literally click the button that says, give me a load balancer. You literally click a button that says, give me 2 servers. You literally click a button that says, give me a firewall, or any number of other features. So Amazon and Microsoft and Google, to some extent, have all implemented these low-level services that still require that you understand the technology, and you understand networking, and you understand scaling and availability, but you so much more easily and inexpensively and efficiently, literally with just a laptop or desktop, without any data center of your own, stitch together the topology or the architecture that you actually want, albeit in the cloud. Platform as a service, though, has arisen as sort of a middle ground here, whereby you might have services like Heroku, which you might have heard of, which themselves actually run on infrastructures like Amazon or Google or Microsoft or the like, but they provide themselves a layer of abstraction that isn't quite as high level, so to speak, as what you get from software as a service. In fact, these platforms as a service don't provide you with applications. They just make it easier for you to run your applications in the cloud. Now, what does that mean? Well, it's all fun and exciting to understand load balancing and understand networking and understand the need for multiple servers and the entire conversation that we've had thus far. But at the end of the day, if I'm a software developer or I'm trying to build a business, all I care about is making my internet application available to real users. I really don't care about how many servers I have, how many databases I have, how the load balancers talk to one another. Like, that's all fine and intellectually interesting, but I just want to get real work done. So I'm willing to pay a bit more for this. I'm willing to pay some middleman, like a Heroku or any number of other services, a platform as a service, to abstract away those kinds of details. So I have the wherewithal and I have the willingness to actually say, host this as a web server. So give me a web server. I will pay you some number of dollars per month to give me a web server, but I want you, Heroku, to deal with the auto scaling of it. I don't care how many servers it is. I don't care how they are connected. I don't care anything about these heartbeats. I just want to have the illusion, for my own sake, of just one server that somehow grows or shrinks dynamically to handle my customer base. Meanwhile, things like load balancing, I just want my customers to be able to reach my server. I don't care how it's implemented. I don't care how it's made to be highly available. I just want that to work. And so companies like Heroku provide these platforms as a service that just make your life a little bit easier. And you don't have to think about or know about or worry about as many of these details. Now, to be fair, if something breaks, you might not understand exactly what's going wrong, and you yourself might not be able to solve it. Indeed, you might be entirely at the mercy of the cloud provider or the PaaS provider to solve the problem for you, but you're saving time, you're saving energy elsewhere by not having to worry about those lower level implementation details, at least in the common case. But odds are you're paying a little more to Heroku than you would to an Amazon directly because they're providing you with this value-added service. So as cryptic as these acronyms really mean, they're really just referring to disparate levels of abstraction, all of which somehow relate to the cloud. But infrastructure as a service is a virtualization of these hardware ideas, the physical cabling that we drew here on the screen. Software as a service really is just that application that the user interacts with, and platform as a service is an intermediate step, whereby you, in building your software in the cloud, can worry about a little bit about how to actually make it available to users. But let's consider one other challenge now, that of database replication. Since, of course, thus far we've been talking about a web server as though it's the entire picture, but the reality is most any business that has a web-based presence or a mobile presence is going to be storing information. When users register, when users check something out, add something to their shopping cart, so to speak, all of that data needs to somehow be stored. So let's consider now what the world really likely looks like. So here is my laptop again, and here is the cloud that's between me and some service that I'm interested in. We'll assume for now that there's some kind of load balancing, and I'm just going to draw it a little bigger this time to sort of suggest that let's just think of it now as a black box, and maybe it's one server, maybe it's two, maybe it's more, but somehow or other load balancing is implemented. And then I'm going to have all of my servers here, which will abstract away as maybe 3 or more at this point, 1, 2, and then we'll call this n. But a web server typically does not do everything these days. In fact, it's been trending for some time to actually have different servers or different virtual machines, or even more recently, different containers, each provide individual services. Sometimes people call these microservices if a container only does one very narrowly defined thing, like send emails or save information to a database or respond to HTTP requests. So these back-end web servers are not the only types of servers we have. Odds are we at least have one database. So let's consider now the implication of all of these architectural decisions we've made thus far on how we actually store our data. So in simplest form, our database might look like this. And for historical reasons, it's generally drawn as a cylinder. And this is our database. Now, it's immediately obvious that if all servers, 1, 2, ... n, need to save information or read information from a database, they've all got to somehow communicate with that database. So they all have some kind of connectivity, physically or otherwise. So this seems fine so long as the software that's running on servers 1, 2, ... n, no matter what language we are using, whether it's Java or Python or PHP or C# or something else, so long as those servers can talk to via the network this database, that's great. They can all save their data to the same place, and they can all read their data from the same place. So everything stays nicely in sync. But what's the first problem that motivated the entirety of this discussion from the outset? Well, what if one database isn't really enough? Well, we could take the approach of vertically scaling our architecture, which is another piece of jargon in this space. So vertical scaling means if your one database isn't quite up to snuff and you're running low on disk space or capacity because of numbers of requests per second are, of course, limited, you know what you can do? You can go ahead and disconnect this one and go ahead and put in a bigger one and therefore increase your capacity. And vertical scaling means to really sort of pay more money or get something higher end, a more premium model, more expensive model that's got more disk space and more RAM and a faster CPU or more CPUs. So you just throw hardware at the problem, not in the sense of multiple servers, but just one bigger and better server. But what are the challenges here? Well, if you've ever bought a home computer, odds are, whether it's been on Dell's site or Microsoft's or Apple's or the like, you often have this good, better, best thing where for the top of the line laptop or desktop, you're going to be paying through the roof, or through the nose, so to speak. You're going to be paying a premium for that top of the line model, but you might actually be able to save a decent number of dollars by going for the second best or the third best, because the marginal gains of each additional dollar really aren't all that much. Because for marketing reasons, they know that there might be some people out there that will always pay top dollar for the fastest one. But just because you're paying twice as much doesn't mean the laptop's going to be twice as good, for instance. So this is to say, to vertically scale your database, you might end up paying through the nose very expensive hardware just to eke out some more performance. But that's not even the biggest problem. The most fundamental problem is, at the end of the day, there is a top-of-the-line server for your database that only can support a finite number of database connections at a time, or a finite number of reads or writes, so to speak, saving and reading from the database. So at some point or other, it doesn't matter how much money you have or how willing you are to throw hardware at the problem, there exists no server that can handle more users than you currently have. So at some point, you actually have to put away your wallet and put back on the engineering hat alone and figure out how to not vertically scale, but horizontally scale your architecture. And by this, I mean actually introducing not just one big fancy server, but two or more maybe smaller, cheaper servers. In fact, one of the things that companies like Google were especially good at early on was using off-the-shelf, inexpensive hardware and building sort of supercomputers out of them, but much more economically than they might have had they gone top of the line everywhere, even though that would mean fewer servers. Better to get more cheaper servers and somehow figure out how to interconnect them and write the software that lets them all be useful simultaneously, so that we can instead have a picture that looks a bit more like this, with maybe a pair of databases in the picture now. Of course, we've now created that same problem that we had earlier about where does the data go? Where does the traffic or the users flow, especially now where we have one on the left and one on the right? So there's a couple of solutions here, but there's some different problems that arise with databases. If we very simply put a load balancer in here, LB, and route traffic uniformly, say to the left or to the right, that's probably not the best thing, because then you're going to end up with a world where you're saving some data for a user here and some data for a user here just by chance, because you're using round robin, so to speak, or just some probabilistic heuristic where some of the traffic goes this way, some of the traffic goes that way. And that's not so good. OK, but we could solve that by somehow making sure that if this user, user A, visits my website, I should always send him or her to the same database. And you can do this in a couple of ways. You can enforce some notion of stickiness, so to speak, whereby you somehow notice that, oh, this is user A. We've seen him or her before. Let's make sure we send them to this database on the left and not the one on the right. Or you can more formally use a process known as sharding. In fact, this is very common early on in databases and even in websites like Facebook, where you have so many users that you need to start splitting them across multiple databases. But gosh, how to do that? Well, back in the earliest days of Facebook, what they might have done was put all Harvard users on one database, all MIT users on another, all BU users on another, and so forth, because as Facebook, you may recall, started scaling out initially to disparate schools. That was a wonderful opportunity to shard their data by putting similar users in their respective databases. And at the time, I think you couldn't even be friends with people on other schools, at least very early on, because those databases presumably were independent, or certainly could have been topologically. Or you might do something more simple that doesn't create some problems like isolation there. Maybe all of your users whose last names start with A go on one server, and all of your users whose names start with B go on another server, and so forth. So you can almost kind of hash your users, to borrow a terminology from hash tables, and decide where to put that data. Of course, that does not help with backups or redundancy, because if you're putting all of your A names here and all of your B names here, what happens, God forbid, if one of the servers goes down? You've lost half of your customers. So it would seem that no matter how you balance the load, you really want to maintain duplicates of data. And so there's a few different ways people solve this. In fact, let me go ahead and temporarily go back to that first model where we had a really fancy, bigger database that I'll deliberately draw as pretty big. And this is big in the sense that it can respond to requests quickly, and it can store a lot of data. This might be generally called our primary or our master database. And it's where our data goes to live long term. It's where data is written to, so to speak, and could also be read from. But if we're going to bump up against some limit of how much work this database can do at once, it would be nice to have some secondary servers or tertiary servers. So a very common paradigm would be to use this primary database for writes, we'll abbreviate it W, and then also have maybe a couple of smaller databases, or even the same size databases, that are meant for reads, abbreviated R. And so long as these databases are somehow talking to one another, this topology will just work. This is a feature known as replication. So long as the databases are configured in such a way that anytime data is written to the primary database or the master database, that data gets replicated to any replicas, as they're called. Meanwhile, servers 1, 2, and n should also be able to talk to these replicas. And if your code is smart enough, and you would have to think about this and design this into your code base, you could ensure that anytime you read data from a database, it comes from one or really any of your replicas. Replicas in the sense that they are meant to have duplicate data. But anytime you write data, a SQL insert or update or delete, as opposed to like a SQL select, you only send your write operations to the primary or master database and leave it to it to then replicate it to the read replicas. Now, of course, there are some problems here. There's some latency potentially. Maybe it takes a split second. Maybe it takes a couple seconds for that data to replicate. So things might not appear to be updated instantaneously, but you have now a very scalable model in that if you have the money to spend, you can even have more read replicas and have even more and more read capacity. Of course, you're going to eventually bump up against a limit on your writes, at which point we need to introduce another solution. But again, this is a very incremental approach, and we can throw a little bit of money at the problem each time and a little bit of engineering wherewithal in order to at least get us over that next ledge, which is super important, certainly when you're first building your business. If you don't necessarily have the resources to go all in on things, you at least want to get over this hurdle, or at least build in some capacity for the next load of users. So what if we run out of capacity, though, with that writable server, the master database, so to speak? We need to be a little more clever. And it turns out we can borrow this idea of these horizontal arrows here to replicate our data, but for a slightly different purpose. We could still have a pretty souped up writable database, but we could have another one, maybe identical in its specs, writable, but somehow these things need to be able to synchronize with themselves. And maybe there's still some read replicas over here, R for read, and another one over here, R for read. And these are all somehow interconnected as well. But you can have what's called master-master replication, whereby your server's code writes to one of these servers. And maybe it's either of them now. Maybe the load balancer actually does send some of the writes this way, some of the writes this way. But the master databases, the writable ones now, are configured in software to replicate horizontally, so to speak. So here, too, you might have a little bit of latency. It might take a few milliseconds or seconds for the data to actually replicate. But at least now we've doubled the capacity for our writes so as to handle twice as many writable operations. And we can continue to hang more and more read replicas off of these if they want in order to handle more and more users. And so this is the sort of challenge and dare say the fun of engineering architecturally, understanding some of these basic building blocks. And even if you might not know the particular manufacturers or how you physically configure these servers or how in software you configure these servers, at the end of the day, these really are just puzzle pieces that can somehow be interlocked. And these puzzle pieces can be used to solve more and more interesting problems. But to our discussion of PaaS and software as a service and infrastructure as a service, there's also these different layers of abstraction. And so thematic throughout this and all of our discussions has been this layering. Indeed, we started really down here with those zeros and ones and bits, and very quickly went to ASCII, and very quickly went to colors and images and videos and so forth, because once you understand some of those ingredients or puzzle pieces, can you build something more interesting? And then can you slap a name on it, sometimes cryptic, like IaaS or PaaS or SaaS, but at the end of the day, those are just labels that describe really black boxes, inside of which is a decent amount of complexity, a clever amount of engineering thought, but ultimately a solution to a problem. And so in cloud computing, do we really have this catch-all phrase that's referring to a whole class of solutions to problems that ultimately are all about getting one's business or getting one's personal website out on the internet for users to access, whether via laptops or desktops or mobile devices and more. So at the end of the day, what is the cloud? It's this evolving definition. It's this evolving class of services that just continues to grow. But each of those services is solving a problem. Each of those problems derives from plugging one hole in a leaky hose, seeing another one spring up, and then addressing that one, and then layering on top of those solutions these abstractions and ultimately some marketing speak, like cloud computing itself, so that you can build out of these more sophisticated puzzle pieces bigger and better solutions to actual problems you have when you're trying to build your own site.